Thank you, Pat. And everybody, I welcome you to a webinar from the American Nuclear Society's Risk-Informed Performance-Based Principles and Policy Committee, RP3C, we call it. My name is Prasad Kadambi, and I'm chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We've been calling these methods RIPB approaches. There's a lot of guidance available on RIPB approaches, but most people have not had reason to become familiar with the guidance because the conventional approaches still dominate most things that we do, including standards development. RP3C initiated these community of practice webinars on RIPB to enable practitioners of RIPB methods to share their knowledge and experience. We have scheduled these webinars for the last Friday of every month. Recently, we've been promoting use of systems engineering concepts and practices as a framework for RIPB methods. Last month's presentation was from ASME's Ralph Hill on the plant systems design standard along these lines. Today, we will hear from Ed Wallace on how ANS is trying to adopt some of these concepts. In particular, Ed's presentation is related to a very important standard, ANS 30.1 on RIPB design process. It gives me great pleasure to introduce Ed Wallace as someone I've known for several decades, but more importantly, helped me set up and stand up RP3C. He has served as its vice chair until quite recently. So Ed, you're on.
Thank you, Prasad, for the kind introductions. Am I audible for everybody? Good. Today I'll be talking about the licensing modernization project. However, as the title suggests, I don't see RIPB processes as a bolt-on activity to a modern design. I see it as an essential part of an effective design developed using systems engineering principles that have already been discussed quite well by Kent Welter and Ralph Hill in prior community of practice webinars. So let's get on with it. A brief disclaimer, as always, the comments that you're going to hear are my comments. In some cases, I have used referenced material that's shown on the slides, but the inclusion of these materials or exclusion of materials or completion of the references is my obligation. I have made no attempt to fully cite to all of the sources, or in some cases, the original sources. I just use recent sources that are available to me. Just a brief introduction. I'm not going to go through all this, but I spent 50 years in this industry in a wide variety of all the different kinds of entities that are involved. I have a technical background from the Naval Academy and other graduate studies, as well as a business background. As Prasad noted, I have been a member of ANS since 2004, but more directly involved with risk-informed performance-based advanced reactor work since 2004. I was a member of ANS 53.1 working group in the development of that standard for gas reactors, which was, I would argue, is prototypical of the general technology inclusive work that's being done today. I want to start with a slide that I've used periodically. Never confuse safety and licensing. This encapsulates one of the major findings from the TMI-2 Accident Presidential Commission in 1979. The responsibility for safety lies first and foremost with the design and operating companies that own and operate these plants. The NRC has an important role in reviewing that work to determine that reasonable assurance of adequate protection is achieved in the design as well as in the continuing operation of the plants. The objective of the LMP guidance in 1804 is to provide a well-structured means to address novel designs that are outside of the framework established for large light water reactors. The technology inclusive content of application, TCAP, is about how to use the LMP more efficiently and effectively to present and confirm an affirmative safety case that reasonable assurance of adequate protection is achieved in a license application. Brief overview of the licensing modernization project. This was a collaborative industry effort led by Southern Company and co-sponsored by Department of Energy. It began in 2016 and completed in 2020 following the final endorsement of NEI 1804 in NUREG, Reg Guide 1.233. This presentation presumes familiarity with the LMP methodology and use of LMP specific terms and uses LMP specific terms where appropriate. NEI 1804 contains a glossary of terms that were developed in part to differentiate new meanings and terms from some historical or previously not completely standardized terms. The LMP purpose, as I just described, is based on regulatory application requirements. It's based on systems engineering requirements and so forth, as I described. It talks about what are the plant initiating events, the event sequences, and accidents, and that are associated with design. It answers the questions about how does the proposed design and its SCs respond to initiating events and event sequences. It addresses the margins that are provided in the facility's response as it relates to prevention and mitigation of radiological releases within prescribed limits for the protection of the public. It also addresses whether the philosophy of defense in depth is adequately reflected in the design and operation of the facility. The first few slides start with the nexus to the systems engineering process. This slide is a figure from the NGNP Defense-in-Depth report. It represents the first step in systems engineering processes, as you've heard, in the development of user and generic requirements for the project. When properly completed, these are the highest level of performance-based taxonomies of information that are created for a project. The top level requirements developed, there's a series of other activities that takes place in any traditional design process. This is completed principally in the pre-conceptual, conceptual, and preliminary design phases, as shown in the yellow spaces. With the addition of modern risk processes, the additional capability to examine the design using PRA tools brings insights on the safety performance of the integrated plant and clarifies or clarifies risks and safety significant features that should be modified, added to, or considered for special treatment in the process of design completion. One note here is when done early, the PRA development should mature along with the design maturation. This is both possible and expected in the latest PRA standards for non-LWRs, as it is recommended in the LMP documentation. As the fidelity of the design matures, so does the development of the PRA, hence the iterative cycle that everyone would expect. This picture is a draft that's being considered by ANS 30.1 working group. It was provided courtesy of Ralph Hill. It does a good job of recognizing the overlapping activities that contribute to any design and the stages of maturation that it goes through in broad terms that the information needs to complete. Systems engineering practices create the structure to build risk-informed, performance-based safety into designs as opposed to prescriptions. LMP assumed that this would occur somehow. The point of somehow is that the design control practices are the purview of the developers, and LMP intentionally left the flexibility of how to do it well up to the people who apply the LMP methodology to a specific design. So there's a limitation in the amount of information in the guidance so that it's not prescriptive. Three points from the slide that can be brought out. First, for the historians in the group, you should appreciate that General Atomics developed their version of risk-informed performance-based processes as part of their systems engineering design control process nearly 40 years ago. The current LMP advances the ball on a number of fronts, taking into account other things such as PRA, capability improvements, development of defense-in-depth evaluation strategies, etc. Second, the precision in which the tasks are done on the PBMR figure is how they build risk-informed performance-based insights into the MHTGR design. Too bad life isn't that simple, as reflected in this simple illustration. Leads me to my third point. Modern plants may have 50 to 100 systems, much like large LWRs. They may be physically smaller, but they still functionally are different kinds of systems and functions. So it's not uncommon to have systems in different phases at different times in the course of a design development. The design matures for a given system at a different time, and depending on the master project logics, sequences. A competent systems engineering program keeps all the interfaces and functional capabilities aligned as the total design matures. That is part of requirements management. Building it into the design control process is a developer responsibility, and standards can help too. Note that the evolution of design details here, this is, again, courtesy of Ralph Hill's presentation. This implies a sequence of events similar to what was presumed in developing the specific tasks in LMP, as seen in the next slide. Before I go to the next slide, I can take a breath here, take a sip of water, and see if there's any questions on the basic foundations that we're going to talk about further. Okay, Pat, any written questions?
There's one
Yes.
question that has come up in the Q&A. This is Dennis Haneke asks, can you provide a document besides ANS 30.1 that describes quantitative defense in depth?
Quantitative defense in depth, and we'll come to that later in this presentation, to the degree that it is written down, is part of plant capability defense in depth in 1804. So if that is sufficient answer for now, let's hold that follow-up, what may be a follow-up question when we get to talk about plant capability later in this presentation.
Yeah, this Dennis, I guess the defense in depth that you're talking about is qualitative, not quantitative. 1804 defense in depth is, for programmatic is, or for plant capability is qualitative.
Well, let's agree to disagree for the moment, Dennis. And I don't want to put the question down. I really would like to have a little bit more of the discussion in hand, so to speak, when we get to plant capability discussions and as part of the defense in depth segment of this presentation.
Sounds good.
Okay, thank you.
And thank you for stepping in, Prasad. We do have a couple other questions, and I will go ahead and I will just phrase, I believe it's Fernando Ferrante with EPRI. While focused on design, there should be a note that design and PRA do not end on construction and startup. PRA in particular is a living activity.
I agree. Not a question. I think that's a very accurate statement. And one of the things that is important, which we'll touch on at the end, is the importance of understanding that baseline as you transition out of the design phase into construction and operational phases with the presumption that the license is already in hand. This is really built around a Part 52 concept as opposed to a
Yeah, this is Fernando. Can you hear me?
Yes.
Yeah, it was just in the previous figure you had it. You know, some people could look at that and think it kind of ends in startup, but it's a continued thing. And I know that's not the intent, but just a comment so folks don't think PRA is a one thing and done.
No, it's a great comment, and I agree with you completely. It also points out that in times past, for the existing fleet, when PRA came into existence and application for the large light water reactor, all the concrete and steel was in place, all the procedures were in place. It was really a look back at the plant. And what LMP is trying to do by including it in a standard plant design, systems engineering driven design, is build it in up front, in part because we believe that there's more value to be gained out of doing that than gained in backfit examinations of plants through the PRA lens.
Yep, thank you.
Okay.
Okay, we have a question from Ralph Hill. The question states, in addition to PRAs, other risk tools such as probabilistic simulation is key in design trade studies and in quantification of system and plant risk.
True statement. And I think it dovetails a little bit with what was just said. There are all sorts of analytical tools available today that provide insights into plant performance. Engineering simulators, control room simulators are all advanced and are being brought forward into the design process earlier and earlier. And they all provide different kinds of insightful capabilities that contribute to the design. They may also contribute to the PRA, and I view them myself as a part of the way you validate completeness. And when I talk at the end about the integrated evaluation of DID, you'll note something in there about the state of knowledge and have we captured those things that are pertinent to this purpose. Have we captured them, or is the state of knowledge incomplete? So anything that adds to that state of knowledge outside the PRA is a valuable contribution to the overall development of the design.
Ed, there is one question about that states, I'm not aware of any quantitative defense in depth standards. Please identify what we have. I'm suggesting that in the interest of just carrying on, because you do have a full presentation and some of these things may become evident later. So we'll hold off on that, and I would invite you to just proceed to the next slide.
That's fine. I will take a very short answer at that question as I understand it, which is I'm not aware of any standards that exist that provide quantitative DID development. I know there's several things in the works, but they don't exist yet. Okay, if I can move on. We're now shifting gears into the LMP methodology. And for those of you that have picked up, so to speak, a 1804 version, there's a lot to be consumed there across all these topics. So what I'm trying to do today is provide a very high-level survey of what the principal products and elements are of the LMP process, and the details I provided, like on this chart down at the lower right-hand side, some reference to a figure number which will take you to a section number where you can get a more complete description of not only what it all means, but in some cases why it exists and how it works with other elements of the LMP process. This view of tasks, and I want to emphasize these are tasks. They're not steps, they're not a sequence, they're tasks. And they have to be completed to reach an integrated final outcome about the affirmative safety case. They include traditional deterministic actions, which are in yellow, PRA, products, and integrated decisions leading to defense-in-depth adequacy determinations. As you can see from this, the actual sequence is up to the design control process owner. The process is iterative within design phases and across design phases as systems mature along the timeline of major segments or subparts of the design. As a general comment on the slides, you can see the note. So if there's anything else that you want to ask about these that's of a very detailed nature, I'll probably defer to the references that are being provided. I might know one other thing about this chart. This chart is an evolutionary chart. It was first developed in the context of ANS 53.1, which is a safety and design process standard for high temperature gas reactors. That was developed in the mid 2000 era and finally put in trial use shortly after, I think it was 2012.
Can I ask a quick question?
I don't know who that is, but yes.
It's Fernando Ferrante from EPRI. On the previous slide, just as a curiosity, so you had tasks that are marked deterministic, probabilistic, or risk-informed. I mean, is
Yes.
that just as a general information? Because, I mean, the perspective I'm coming from is the whole process is kind of risk-informed, and PRA has elements that are deterministic in it and others that are more probabilistic. So I'm just curious about the language and the task coloring, whether that makes any difference or is just something to kind of guide people.
It was intended to be illustrative of how these things blend together and to create a risk-informed design. And the boundaries of these terms is more illustrative than it is dispositive, if I can use an old phrase, for what we're trying to accomplish.
Okay.
Ed?
Was there another quick question?
Well, this is Jim August. I was just going to say that was originally put in 53.1 more as an oh by the way at one of the very last revisions to just illustrate that there were a variety of considerations as you went through this process.
Yeah.
So it's a carryover.
Yeah, I think it is, but it continues to serve a purpose, I think, in today's world, because each of these tasks is described in greater detail in 1804, and to build an understanding of what really happens inside those figures. And then in some cases, some of those figures represent a whole section of 1804. So it's not trivial, but it does provide some holistic view of what it takes to get through the process from a task perspective. So that's really what was intended. The other historical point, I don't mean to belabor this historical point, but to Jim's comment, there was a lot of confusion about the use of PRA for new designs and how to use them. And the work at the time when this was generated the first time was more of a bolt-on mechanism to assess completed designs. So what we were trying to do is emphasize the look forward here and how to build it in as opposed to bolt it on. Okay, if I may move on to the more substantive stuff. This is a figure that was developed from some TCAP work earlier this year, and it's not in 1804, to try to focus on inputs and outputs of the LMP process as they relate to products that have to be generated within the design process. And without going through all of the steps, it really does sort of flow from what you start as your functional design objectives, as I showed in one of those earlier slides, and flows into the development of the PRA and includes not only all functions provided by the design, but context of fundamental safety functions as described in regulatory activities in the past. One point I want to make, which is why I've circled the functions provided in the design, there's a very important step in the early development of the design to do a HAZOPS or something equivalent to a HAZOPS. And that step is really where you catalog all the potential challenges to the design for both safety reasons and other reasons, as well as align all of the functional outcomes of having something that makes something that's of value to the owners and the public. In that process, there may be some conditions which rise to the level of fundamental safety functions that need to be satisfied by a multiplicity of systems and conditions that will be described later. And so a different way of saying this, all the three fundamental safety functions that we all grew up with LWRs and have been treated as sort of co-equals may end up being incomplete or may not be equal. Of equal importance. And it really, in looking at a technology inclusive approach to this, that became apparent to us. So I don't want to diminish this, this feeder into the LMP. It's an essential part that gets done right. I will offer one example just in passing that in my own mind might rise to that same level of occasion. And if you have a sodium plant, the management of sodium is an essential solution, not so much because of radiological transport, but its ability to disrupt the entire plant and create radiological transport, huge fires or whatever. So I know there's technological answers for that, but it permeates the design. So it probably rises to the level of very specific importance in coming up with functional requirements and physical requirements for the plant. I'm going to come back to this chart a little bit later. The one thing not shown on the chart on the right-hand side is that it talks about all of this being inputs to the design and content of the applications, which is true. But again, this was developed to show how LMP would feed the content of application discussion. But what was left off inadvertently, I would say, is also how this all contributes to the defense-in-depth storyline. So if you'll allow sort of an imaginary over on the right-hand side box that says evaluate defense-in-depth as also an input to the content of applications, then we stay on the same page. I want to now shift gears a little bit to the components of the LMP process. There are three essential outcomes of the LMP process. The identification of event sequence families from the design-specific PRA, establishment of safety classification for SSCs, and a determination of risk-informed performance-based special treatment, and the provision of a structured means to evaluate defense-in-depth adequacy. Prior to this LMP effort, defense-in-depth was a philosophy that was defined in philosophical terms and described in broad sweeping terms and regulatory guidance on some of the things they were going to look for. And in the end, defense in depth is what addresses all the residual uncertainties and concerns, just in case the design didn't cover them, if you cut through all the reasons for it historically. So what we've tried to do with the advent of more modern tools and structured design processes that are more thorough, in my estimation, we've tried to take defense in depth out of the philosophy category and move it into a implementable component of the design where it's thought about throughout the design, rather than some judgment is passed on it at the completion of the design. This slide covers the first outcomes with regards to LBE determination and risk significance as part of the output. It's derived from, it also leads to the derivation of required safety functions, which are a key component in coming up with design capabilities at the SSC level. In order to perform any evaluation, a performance-based set of objectives must be defined. For LMP, that performance context is provided by the creation, in part, of a frequency consequence target for the entire plant safety context. The target, and it's specifically called the target because it's not a regulatory limit or criteria. It's something to use by the design team to help assess the design as it's being developed. It's not about compliance. It's to guide other actions to complete the design and then evaluate it later. The target provides that context. As part of the process of defining LBEs and performance, uncertainties in the predictions are also included in the process. I'm going to talk more about uncertainties a little bit later. In addition to the assessment of LBEs, the aggregated plant performance is examined using 3 cumulative risk metrics directly related to public radiation risk, 10 CFR 20, and two metrics involving quantitative health objectives. This slide shows the basic construct of the FC target. The boundary lines and regions provide the risk-informed context for an LMP safety evaluation. Keeping LBE risks low should be an objective of any design because you're also improving, in all likelihood, plant availability and output and other owner objectives for the economic success of the project. It's a natural consequence of also using the LMP methodology early in design. It gives you more flexibility to change the design when the impact on the design is less significant. This slide demonstrates how LBEs can be reflected on an FC curve. These points are reflective of different designs, which is why they're different colors. The points are not final design results, so please don't go back to any organization and say, how come your design for this or that is not this, this dot, it's not, that's not the purpose here. However, they're indicative of insights that are available early in the design to help shape the course of the design development. One point on LBE plots, the uncertainty bands around each of these dots is an integral part of the process. These uncertainties drive supplemental actions to achieve adequate defense in depth. This information is used to guide also used to guide the classification of SSCs, as well as being part of the defense in depth evaluation, looking at things like margins and so forth. So that's the basic construct of the design of the chart. Excuse me. I want to go back to this chart for a minute. The circle on this version of the earlier chart provides some emphasis on the integrated challenge from breaking the functional design outcomes that are more or less on the left-hand side of the chart down so that the designer can create component specification level information and special treatment requirements. These are commensurate with the safety risks. This feeds component specifications using appropriate industry codes and standards, procurement and installation specifications, procedures, quality activities, in various phases of the project for different types of products, including plant testing and so on. My main point on this is where the real money is saved, is getting this right. This is where the maximum economic value of applying risk-informed, performance-based practices is created. Done right, this is also where creating the most meaningful reductions in regulatory burden can be provided, which translates into additional savings in the operational phases of the project. All of this is also without sacrificing the level of public safety needed for the project. So I'm trying to make a distinction here between building it in up front and doing 5069 backfit relief efforts, which still produce quite a bit of value, but I think I'm trying to demonstrate that in the capital cost of the plant and other places, the 5069 retrospective reviews can't change. This is where you change in a forward fit manner. If a prevention or mitigation function of an SSC is necessary to meet a design objective of keeping LBEs within the FC target, you should keep in mind that within the FC target, what we're talking about here is within the line for the XC curve and the 2-decade crosshatched area underneath that line. That's what we're calling keeping it within the targets. That crosshatch line is a triggering condition for evaluation of what is being described in the document as a risk significant SSC. SSCs may also be considered risk significant if an SSC contributes greater than 1% to greater than 1% of the cumulative risk metrics, to any one of the cumulative risk metrics. Risk significant SSCs may or may not become safety-related SSCs. This is described in great deal in NEI 1804, and I'm not going to cover that here, but they're not equivalent. Risk significance is not necessarily equate directly to SSCs. Risk significance does not directly relate to safety-related SSCs. The relationship between safety-related SSCs and non-safety-related with special treatment SSCs requires more extensive conversation than is possible today. This area covered by the red circle, and I'm approximating it here, is also the subject of ongoing work by ANS 30.2 working group. So I'm glad to see that this LMP segment, which could not be defined at the level of the standard, is being picked up within ANS. To take a look at just sort of a summation, this is a composite view of safety categories. Safety-related, which includes, as I've said, safety-related let me start over. Risk significant, which also includes safety-related SSCs, and this shows that some things may not be all associated with risk significant SSCs for safety-related SSCs, and I'll come back to that in a second. It also talks about safety significant SSCs, and it's important to recognize that safety significant SSCs are things that are added to risk significant SSCs. They are beyond, if you will, the domain of potentially becoming safety related with a couple of exceptions, but they are principally added for defense-in-depth reasons. There is some subset of the entire plant that's also modeled in SSCs, which are shown here. And part of the defense-in-depth evaluation is also to take a final look at whether or not there's any other hazards that are in that remainder of plant SSCs that might have some bearing on the safety case. So this is sort of a complete representation of all the things that get captured within the LMP scope, but the defense in depth evaluation doesn't lock itself in to just the PRA model SSCs. It looks at the whole plant. The derivation of special treatments come from functional analysis that are then decomposed further to specific safety-related design criteria. NSRST SSCs are also derived from LMP functional analysis. The distinction is that NSRST SSCs are those that provide additional defense in depth capability that is determined to create greater assurance of public safety. These distinctions are developed in the guidance document in the defense in depth segment. Both safety-related and non-safety-related with special treatment SSCs receive special treatment. However, that treatment can and should be very different depending on the safety significance of the SSCs. Before I go on to this segment, are there any questions on LBEs or SSE topics?
We do have 4 open questions, although I can't say that they're on that specific topic. I don't know, Prasad, is there something you want to pick out of there maybe?
Well, I'd like to, in the interest of making progress through Ed's presentation, just try to catch the flavor of some of this. You mentioned a question relates to 10 CFR Part 20, and asks how about Part 100 limits, so maybe you can quickly answer that, Ed.
Part 100 limits, Part 20 limits were considered in the development of the FC curve. And on one of the versions of the pictures, it actually shows where those limits are, the vertical lines on the chart. How they were used, they weren't. The Part 100 limit was not directly used. What was used was as an anchor point. What was used was the quantitative health objectives, and then there's an inflection point at the Part 20 limits for cumulative dose expectations in the course of a year. That is more fully described in the LMP discussions. Right? Regulatory limits and criteria are regulatory limits and criteria. This is really intended to be the development guidance for designers at this stage.
Right, I think that's the key point.
Right.
So another question says, do those estimates in the FC target account for release dose mitigation actions?
I'm sorry, ask the question again.
The FC target, does it account for release and dose mitigation actions? I think the answer is yes.
And the answer is yes. It's the entire event sequence families, which include preventative actions and mitigating actions that occur at some layer of defense. Now, so it's the total performance, whether it has a mitigative or preventative effect, is something that this next slide leads to discussing. So I'll stop there.
Okay, and then there's a question about, can you discuss how a QA is relied upon to protect assumptions in the system safety case?
Yes, and if you'll bear with me for a couple of slides, I'll show it. Okay, at least in broad terms. Okay, I'm going to go through these last few slides fairly quickly because there's just way too much detail to discuss, but I want to introduce the construct for defense in depth. And so I'm going to start with something that was written down in a NUREG KM 09, authored principally by Mary Bruin. May she rest in peace. But she did a great job in trying to start this decomposition of a philosophy and turning it into an engineering practice with some construct. And this figure, I think, was a great representation, frankly, of the notion of what layers of defense mean, and when considering defense in depth, and also tease out protective measures. And without going through all the words on this slide, we adopted this discussion. In talking about layers of defense, we reflected on the IAEA definition of layers of defense, and with some minor wording changes to get it to align with the wording in LMP, they're the same. It also reflects the notion of you can't prevent everything and mitigate everything with plant features, so it includes layer 5, which is the emergency planning layer. The framework that was developed, and it was developed probably 18 years ago now, this basic picture, really looks at 3 different components of defense in depth. It looks at the plant capability defense in depth, and that has to do with what the physical plant can do for you or do to you, in the case of LBEs, with a fairly quantitative basis. And so it provides things like doses, it provides things like frequencies, it provides a performance-based outcome that you can measure against performance objectives for the plant. And that upper level information at the plant level that's derived from the LMP is then the foundation for propagating, I'm going to ignore that doorbell, propagating those requirements down into the design to the lowest level necessary. There are also some other attributes, which I'll touch on in a minute, in plant capability to look at the plant capability in a qualitative way as well. The second segment is programmatic defense in depth. In order to, in broad terms, in order to keep the design within the design bounds, programs, controls, and other things are required for the operation of the plant. So this helps in the definition of what those programs need to be, at what level of fidelity, and for what purpose. It also allows for other supporting activities to focus on the right kinds of safety issues. It supports the development of procedures. It supports the development of training. It also supports actions that can be taken to improve the state of knowledge while you're in the middle of the design. And that might be something where you have a low level of confidence in a PERT, and you say, gee whiz, I think I need to go do some more testing on my test facilities, or maybe I need a different kind of test facility. And these are things to reduce uncertainties about some aspect of plant performance. These flow through deterministic evaluations because some of it's qualitative. They also flow through the PRA to get risk insights. And they contribute to an integrated evaluation of the entire plant performance as part of the defense in depth. And as I'll describe in a minute, they look at different attributes to make sure that the design is complete, the state of knowledge is high, emergency planning is adequate, and that the normal sources of uncertainties have been reduced to an acceptable residual level. So I've said much of what's on this slide, but I want to emphasize a couple of points here. Low and no dose LBEs are important too. Because they're low or no dose doesn't mean they don't potentially signal a need for some other kind of change in the plan. Two reasons why that might be the case. One is that an LBE in an ALO region with no dose may rely on a feature that is also relied on if certain systems fail and an event propagates to a DBE. In the DBE, you may have a single feature, that same single feature that has to perform, or you end up with a beyond design basis event, and so forth. The LWR example that I use all the time is if your reactor vessel isn't beyond reproach and basically, to use the term, beyond the point of credible failure, then I'm not sure how you ever get through this process. You would never have an acceptable design. But that also argues for why all of the special treatment for reactor vessel integrity in light water reactors is appropriate, because you can't analyze and you can't tolerate the possible consequence. So it's been taken to the point where there's an incredibility of failure. The second thing is, it may be that you have layers of defense available where one layer is not necessarily independent of the next layer, but the collection of layers of defense is adequate to assure public safety. So looking at some of these features in the plant, even though there's no dose, is still intended as part of this process to make sure you understand why you can get design basis accidents that are acceptable, and make sure there's no other conditions for which you are overly reliant in the precursors to the design basis accident scenario. I'm now going to go through a couple of these, three of these attribute tables, and I'm not going to read all this stuff. I'm not going to even try to explain it all, but each of the corners of that triangle before have attribute tables developed for them. They contain both attribute categories and they contain evaluation focus items for these things. Also in the same section, they will contain other considerations that are another layer of detail or another angle to look at the challenge or the attribute. And so you will get into things that are really important, like plant margins, uncertainty in plant margins. And it's not margins, in the case of this defense-in-depth evaluation, to regulatory limits. It's margins to where they're risk significant. Also looking at some other abstractions, such as prevention and mitigation balance. And what I want to really emphasize there is in the LMP construct, that's not within a layer of defense. Reliability is the important focus within a layer of defense of all the functions provided by that layer. What's really looked at is, do you have a reasonable distribution of prevention and mitigation balance across layers of defense? So no single layer, no exclusive feature is part of that. Independence is part of that, and so forth. In the next attribute set for programmatic, and this comes back to a question that was asked, you also look at the performance targets for SSC reliability and capability. You look at special treatments such as quality assurance programs, testing programs, or other treatments to demonstrate that you're going to be able to meet the expectations of the design. How much of that's required can be and should be a risk-informed answer, because not all components have the same risk significance. So when you get down to SSC or subsystem reliability goals and functions, you can look at them and look at the contribution of components and say when to stop. That's sort of the 5069 analysis forward fit view of it. In 5069, that's what people did to try to get out of special treatments that didn't really deal with components that had any safety significance. This is also where you look at compensation for human errors and making sure that human reliability has been properly factored in, and that the human factors program for any safety-related actions that operators have to take have been properly addressed. You look at mechanical errors, you look both in failures or degradations of performance. This is an important component if you're using passive components, because passive components don't turn on or off, but they do have the potential to degrade and drift outside their operating design envelope. You look at, also look at knowledge uncertainty. You can't know everything about everything. So this is really a search for the reduction of your uncertainties to the point that residual risks are acceptable. And again, that's knowledge uncertainty. And goes also to the completeness, confidence you have that you've got a complete solution. And then finally, you still have emergency response capabilities, and you look at that as a compensation for residual uncertainties. You also look at it in the light of your design basis accidents, which are contrived, I might say. They are special cases that are outside of the frequency consequence curve often, but particular frequency curves. And you look at whether or not under that more limited state of responses, you still have acceptable capabilities, and you know how and when to actuate emergency response features. Finally, the integrated evaluation sort of goes back to the beginning with the risk triplet to say, do I really have a complete understanding of what can go wrong? How likely is it? What are the consequences? This is not to repeat any of the work that's done by the line organizations in coming up with the design in the first place. It's to just step back away from it at some point in time and say, are we sure about these answers to this question being complete? It talks about other tools, which came up in a question. And I personally am very impressed with the capability of engineering simulators today. When I joined NuScale and said, how does it work? They happen to have the first edition of their engineering simulator for one module, and it would provided a wealth of information. And one of the things that it provided, and this is a true life story, we were running a simulation. Friday afternoons are my time to do this. We were running a simulation, and we simulated a loss of everything event. And by that we meant we turned off all the heat removal, and we didn't let the rods go in. We just took all that stuff away and said, what happens to the plant? How can we melt it? And lo and behold, we discovered two things. One is it's really hard to melt it. And the second thing is, if all of the engineered safety features and everything else fail, your safety valves work. And so even if one of them doesn't work, or even if they stick open, which is the predominant failure mode, that's okay. The plant will not uncover fuel or melt fuel. So these are things that I think come into play, and you need to be attuned. And I think this process is intended to make sure people are attuned to this kind of process. I've talked about sources of uncertainties enough. The last final point I want to make, in the LMP guidance, there is a discussion about action refinement, and that includes practicality and effectiveness and cost benefits and other considerations that every designer, every owner and operator has to deal with. But the principal objective here is, if you can conceive of something to do, you have to also, or should also, ask yourself, does it move, if you will, the risk needles in some manner? For the metrics that you're using, does it make a material change? Does it push you from outside of the risk significance zone to where, even with your quantified uncertainties, you're now inside the uncertainty, the risk significance zone? And if so, what do you do about it? So it's a thought process. It's a very qualitative, deterministic process, but it's part of the process. So the fact that NRC understands this in the endorsement process, I think, is a real plus for people who are trying to use this to complete designs and get into licensing. Finally, this is just an overview of the kinds of things that show up in each of these boxes that I just sort of described in terms of information that can be used at some point in time to complete the design or complete the licensing. I'm not going to go through it, but it's here for your reference. Finally, two other quick points. One is a note on terminology. I've touched on it already. This slide highlights some specific, but not all the specific LMP terms that we put in the glossary. We've been encouraging everyone to use them if you're applying LMP, not use some equivalent or some other old term that might not match with what's intended here. It's important because the definitions and the use of these terms in the execution of the LMP will lead you to where LMP is trying to lead you. And if you don't, if you interpret them and they become broader or less complete, then it's hard to tell where that might lead you. The second thing is, and I say this in the context of standards as well, not just of applications people, please use the terms unless there's a problem with the term or there's some other terms you need to add for the purposes of what standards you're writing to make these terms work. Also, there are some specific things that are intentionally omitted in LMP. I've touched on a few of them here: single failure, important to safety, credited. Credited is a term that says I didn't consider a whole plant. LMP considers the whole plant capability. So we never use the word credited in LMP. And as you know, 5069 risk categories have four boxes, and part of the objective of this is to not have 4, have 3, and not have a safety related with low safety significance. So we think we've accomplished that, and the endorsement of the reg guide, I think, confirms that the staff is satisfied, at least now, to the level of information that's been provided. Future standards activities that focus on risk-informed and performance-based incorporation should adopt these terms or build on them, as I said. But creating alternative terms is probably only going to add to confusion within the industry and confusion for any applicant that takes it to the regulator, because you'll have to explain it. Last thing, I've provided a set of references. The last references are Southern Company documents, previously known as the LMP white papers. They were completed as part of this project. Here are the reference numbers. They were intended to be put in DOE's OSTI along with the final products here. We caught that in me drafting this presentation. They will be shortly so that they are publicly available and referenceable if you choose to use them. They contain a lot of other examples, and I'll talk about the last one, which is a lessons learned document. That's just a table of contents from the lessons learned document to give you a sense of lessons learned, best practices that were uncovered or recognized in there. And most importantly, frequently asked questions. And several of the questions that are raised here have more detail in there. And there are ways to weave your way through LMP sections, which are structured in a different manner to get the things that integrate components of the LMP program together, maybe in a little bit better way to understand it. Thank you very much. Are there any further questions for the time that's not remaining?
Well, we are a bit over the time, Ed. I want to thank you very much. The thing is, I did have to move things along just to make sure that you got through all your slides, and I apologize to the questions and comments that we haven't gotten to, but we will try to get back to you with some kind of responses to them. So while I still have you on, I'd like to mention that the community of practice sessions for November and December are going to be canceled because they fall on at times that conflict with the holidays. So we will pick back up on the last Friday of January of 2021. So since we are a bit over the time limit, I want to thank everybody for participating in this community of practice session. And, if you have any other questions or suggestions, please do forward them to either Pat Schroeder, who's the standards manager, or myself as chair of RP3C.